These are our notes on our little mini unit on specific heat. I want you to watch these before you come to class so that we're ready to do practice problems and do our first formal lab that you guys are going to do on your own. So let's talk about specific heat and talk about energy. So energy is the capacity to do work or produce heat. So anytime we're talking about heat or temperature or anything like that, we're talking about energy. So energy is really important in chemistry. The law of conservation of energy, just like the law of conservation of mass, states that energy can be converted from one form or another, but cannot be created or destroyed. So very similar to the conservation of mass. So the energy in the universe is constant. When we look at energy and we look at studying energy in our class, we're going to use calorimetry, and it's just the method by which heat quantities are determined, where we've got something cold or hot that's placed into water, and we're looking at the change in temperature of the water. Most of the time what we're going to do is place hot objects into cold water and take the temperature change of the object and the water to figure out our energy. So we always know that heat flows from hot to cold, so this is an exothermic example here, and we're going to use exothermic examples in our lab. So heat flows from hot to cold, so the water we're going to assume is going to heat up, which we'll be able to use to calculate our values in the lab. We're going to use 2 styrofoam cups placed together as our calorimeter. We have a poor man's calorimeter in our chemistry class, so we assume that it's perfect, but definitely in our calculations we're going to be a little bit higher on our percent errors because it's not a perfect calorimeter. So some things when we study calorimetry, what we need to know is this thing called specific heat, and it's the amount of heat energy required to raise the temperature of a substance 1 joule per 1 gram of a substance and raise it 1 degree Celsius. So specific heat deals with joules and energy, and it deals with a gram of a substance, and it deals with degrees Celsius. Heat capacity is the amount of heat energy required to raise a given quantity of a substance, so mass times specific heat. So when we want to look at heat gained or lost, we use this equation right here, energy equals mass times Cp, which is again the specific heat, okay, times the change in temperature. And Q can be a negative or a positive number, and we'll talk about that in just a minute. So let's look at a practice problem here. How much energy does it take to raise 10 grams of liquid water from 5 degrees Celsius to 50 degrees Celsius? So what we want to do is remember that our equation here is mass times Cp times change in temperature. And so the first thing that we want to do is find what is our change in temperature. So change in temperature is always T final minus T initial. That might be a really good equation to remember because you're definitely going to have to use that on your lab. And so that should be an equation that shows up in your background section because you're using that to find your change in temperature. Remember, even simple mathematical formulas show up in your background section. So in this case, our change in temperature is 45 degrees Celsius. Then what you're going to do is set up, I want it to look in a T-chart, please, so I want you to set it up in a T-chart so you can see how things are crossing out. So what I know is I have my mass, which is right here. My mass is 10 grams, so I'm going to include it right there. My Cp of water is 4.1, and I actually want it to be 4.184. That's the more correct value. And it's joules per 1 gram per 1 degree Celsius. There's an implied 1 down here. And then we're going to include our change in temperature, which we just calculated. So then what we can look at is how things cross out. So my grams cross out, my degrees Celsius cross out, and I'm left in joules, which is our heat energy value for Q. And my answer ends up being 1,180 joules or 1.88 kilojoules. I don't care how you represent it if I don't ask. So it's helpful to look at some context of specific heat in terms of relative substances, and that's also what we're going to be studying in the lab. So specific heat of metal and rock is less than 0.8 joules per gram degree Celsius. So kind of think about how fast metal and rock heat up. So if it's got a low specific heat, it probably doesn't heat up very fast, or it probably heats up very fast, and it actually also cools down very fast. So if it's got a low specific heat, that means it does not take a lot of energy to heat it up, and it also does not take a lot of energy for it to cool down. So if you look at wood and think about what do we use in terms of cooking, we use metal to cook with and like wood spoons to stir because that specific heat is a little bit higher, so that substance isn't going to heat up as fast. It's also not going to cool down as fast. Water, relative to the other two, has a really, really high specific heat. It takes 4.184 joules to heat up 1 gram of water, 1 degree Celsius. And if you remember from our lab technique lab, 1 gram of water is the same as 1 mil of water. And so that's a lot of energy to heat up water. And if it takes 4.184 joules per gram degree Celsius to heat up water, so it takes a long time to heat up water. It's probably also going to take a long time for water to cool down, because the same amount of energy is going to be released when water cools down. So that's definitely something to think about there. Alright, so assuming that our calorimetry is perfectly insulated, we know that our calorimeter is equal to the system. So we want to look at our water and our object as a whole system here. And we're assuming that the styrofoam, again, in the top of a cup doesn't lose any heat, but we definitely know that it does in our lab that we're going to be doing. So again, when we look at calorimeters and the calorimeter constant, we're disregarding any heat absorption for our perfect calorimeters, but that's definitely always counted as a source of error. So defining the specific heat of a metal, this is exactly the math that you're going to do in the lab. So I'm going to actually walk you through how to do this on the next slide, and it's just a blank slide, and that'll actually help you do the math for the lab. So I recommend that you copy this down on your PowerPoint notes somewhere where there's some blank space, because this will help you refer back to this calculation and these calculations for your lab. So an iron bar of mass, 70.5 grams, cools from 100 degrees Celsius to 21 degrees Celsius. So what we're going to do first is actually heat up some objects, and so we're going to heat up an object to, let's say, 100 degrees Celsius. And we're going to put it into cold water. And we're going to assume that that water is 21 degrees Celsius, because if you notice, the water and the water temperatures are the same here. So the water started at 15 degrees Celsius and went to 21 degrees Celsius. So it started at 15 and went to 21. We're going to heat up an object, and we're going to place it in 100 mils of water. Remember, 1 mil is 1 gram, so that's going to help us with the mass. So what we want to do is figure out, using our specific heat of water, our mass of water, our change in temperature of water, we're going to figure out the specific heat of the metal. And again, this is exactly the math that you're going to do in the lab, so pay attention. So what we want to do is set up our equation. So we know that the energy released by the object is going to be equal to the energy absorbed by the water. And this is really, really important. And we know that energy is equal to Q is equal to mass times Cp times change in temperature. So if the energy that's released by the metal is equal to the energy absorbed by the object, I can assume that mass times Cp times change in temperature is energy. And I'm going to apply both of these calculations and just set them equal to each other. So right here I know that the mass of the metal times the Cp of the metal times the change in temperature of the metal is the energy released by the metal. And because I know that the energy released by the metal is equal to the energy absorbed by the water, I can actually set that equal to the mass of the water times the Cp of the water times the change in temperature of the water. So then what I can do is look at my values from the previous slide and plug in my calculations, and I do want to see it as a T-chart. And this would also be a great thing to include in your background section for your specific heat lab, because that's a calculation that you're going to use quite a bit. So I know that my mass of my object was 70.5. I know the mass of my object was 70.5. I'm trying to find the specific heat of my object, and I know the temperature change was 79 degrees Celsius because I calculated the temperature change of my metal. So remember, temperature change, anytime you're calculating something, that should show up in your results section. I also know that my mass of my water was 100 grams because 100 mils is equal to 100 grams. I know my specific heat of water is 4.184 joules per gram degrees Celsius, and I know my temperature change of the water is 6 degrees Celsius. You're always going to have a larger temperature change of the object, and you're always going to have a smaller temperature change of the water to help you in your calculations. So now once you see that, you see you have one variable to solve for. So you solve for the specific heat, and the specific heat of that metal is 4.15 joules per gram degree Celsius. So that's how we can figure out how to solve for our unknown specific heat of certain objects. And the object doesn't necessarily have to be metal. We're going to work with dice and marble and clay and things like that in the lab, so it's not necessarily metal. Really, the correct term should be just the energy released by the object. So this is just talking about, again, energy absorbed equals energy released, and looking at the law of conservation of energy. So in all reality, we shouldn't lose any energy, but again, we have poor calorimeters, and so we're not going to have perfect examples here. Again, this is an excellent pre-lab equation that should be something that should show up in your background section of your formal lab that you're going to write here. So this is just stepping through finding the specific heat of the metal and then finding the specific heat of the water. So this is just stair-stepping through exactly what I showed you on the blank slide before, where you're calculating out the energy absorbed by the water, and then you're calculating out the energy released by the object, and you're able to set those equal to each other and solve for the specific heat of the object. Feel free, like I did on mine, to put it all into one and just solve for that one variable in just one step. The last thing that we want to talk about is just enthalpy. So we need to understand that anytime something is releasing energy, we represent that with a negative number. Anytime something is absorbing energy, we represent that with a positive number. So when heat is flowing out of a system, it's exothermic, and we represent that with a negative. And when heat is flowing into something, we represent that as heat being absorbed, and we represent that with a positive sign. Okay, so you're ready for our specific heat practice problems and our specific heat lab that we're going to complete. Thanks for listening.